Welcome to Dialogues of Discovery, a platform where we bring you conversations with visionary thinkers and trailblazers who are shaping the future. If you are curious, passionate, or just figuring it all out, you are in the right place.
Each episode brings you insights, experiences, and advice from the lives and minds of remarkable people scientists, innovators, and creators. So you can get inspired, explore, and start carving your own paths forward. Listen on to uncover more.
Today, we have the pleasure of speaking with Professor Pawan Sinha, a professor of vision and computational neuroscience in the Massachusetts Institute of Technology, Department of Brain and Cognitive Sciences. His research explores how the brain learns to see to make sense of the visual world, with a particular focus on visual perception, object recognition, memory, and developmental learning. Combining neuroscience, computational modeling, and artificial intelligence, Professor Sinha has made pioneering contributions to our understanding of how vision develops, particularly through his groundbreaking work on congenital blindness and visual recovery.
Alongside his research, Professor Sinha is widely recognized for leading Project Prakash, a remarkable initiative that combines humanitarian eye care for children with congenital blindness in India with cutting edge scientific research into brain plasticity and visual development. His contributions have earned him numerous prestigious honors. He is also the co founder and chief scientist of Edify, where he applies insights from neuroscience and AI to help students discover their interests and make informed educational and career decisions.
Well, what are we waiting for? Let's get started. Hi, sir. Thank you so much for being a part of us. We would like to start off with telling us a bit about how you got into biomedical and also learning about neurology and helping people see and also understanding how the brain learns to adapt. So, could you help us understand how your early interests began and where you are now?
Sure. It's a pleasure to be here. Thank you very much for inviting me to be part of this dialogue. I had a fairly conventional education in India. I went to DPS Arkipuram, and then after 12th grade, I did my undergraduate work at IIT Delhi in computer science and fairly mainstream computer science. So when it was time for me to think about next steps beyond my undergraduate work, what was clear to me was that I wanted to engage in higher studies, but my horizons were still kind of defined by what I had done, which was computer science. So I applied to PhD programs in the US with that idea that I want to specialize in high performance computing. And I was fortunate to receive offers from several very nice universities. I chose to go to UC Berkeley in California. And there I started my PhD work in computer architectures, hardware. And even though that's important work, in fact, many of the advances in our world are driven by advances in hardware, I was finding that it wasn't really engaging all of my interests. And in that frame of mind of trying to understand what it is that really resonates with me, something that I would want to spend the rest of my life doing, it so happened that at that time, an elderly professor at Berkeley, who had incidentally won the Nobel Prize in physics for having invented the bubble chamber, he had gotten interested in neuroscience and he wanted to learn more about neuroscience. In the best spirit of the best way to learn a topic is to try to teach it, he offered a seminar in neuroscience, which was open to any student, any faculty member. And I started sitting in that seminar, and it was a very broad-ranging discussion of open questions in neuroscience. And the more I learned about neuroscience, all of the challenges, all of the interesting subfields of neuroscience, the more I fell in love with it. So I decided that that would be the focus of my work. And with that idea, I started taking classes in neurobiology and neuroscience. At that point, I felt that instead of completely giving up on my background in computer science, it would be nice to try to combine my newfound interest in neuroscience with my training in computer science. So I would want to work in computational neuroscience. Berkeley at that time did not have a very strong program in computational neuroscience, but MIT did. So with that idea of working in computational neuroscience, I transferred to MIT after a year at Berkeley. And here, even though I was formally in computer science, the focus of my work was more on the neuroscience side of things. And then after completing my PhD, when I transitioned to my postdoctoral work, then I formally shifted to neuroscience, to the Department of Brain and Cognitive Sciences. And then after my postdoc, after a brief stint as a faculty member at the University of Wisconsin at Madison, I was fortunate to get an offer of a faculty position right here at MIT in Brain and Cognitive Sciences. And I've been here ever since. So I've now been on the faculty for about a little over 26 years, and I've loved every moment of it. The field of neuroscience is fascinating, and this place, MIT and Boston more generally, it's one of the most interesting places to be in, to be able to conduct cutting edge research in this area. So that's roughly my trajectory.
I think that's a really interesting way your journey has progressed, going from a background in computer science, which at that time was kind of the thing that everyone was doing, and now where you are, where you've learned to, or you've decided that this is something I'm interested in, and I'm going to use what I know to progress in that field. I think that's really amazing, and I probably what a lot of us aspire to do today. Now, you spoke about neurobiology, neuroscience, but I was reading about your work and I noticed that a lot of it was about how the brain learns to see, how it adapts when it's related to vision, right? So just wondering what actually inspired you, what led you down that particular path, like that niche of neuroscience.
Yeah, so from one perspective, it's a niche, but from another perspective, it's a large chunk of what the brain does. So I suppose, again, zooming out, if you were to think about what it is that the brain is really good at, what it's good at is learning. Neuroscience as a field, in very broad terms, is an attempt to understand how we understand the world. And the brain doesn't come with all of the knowledge about the world. It has to acquire that knowledge through experience. It has some preset architecture, but that architecture changes in interesting ways, and the brain learns to make sense of the world. And this learning is most evident during development. We keep learning all through our lives, but during those early months and years, that's when the learning is most impressive. And even within this very impressive set of developmental progressions, to my mind, one of the most impressive developmental progression is that in vision. Our ability to make sense of the world from visual input. One interesting factoid about the primate brain, about monkeys and humans and apes, is that a huge amount of our brain is devoted to processing visual information. Something like a third of our brain is devoted to visual information processing. And we would love to understand how it is that the brain comes to acquire its impressive visual capabilities. How is it that the neurons that are responsible for visual processing, how do they come to acquire their specializations, the functional capabilities that they have? So if you look at the developmental progression for an infant, you find that within a matter of about 6 to 7 months, a baby goes from being this helpless little newborn to being a pretty sophisticated observer of the visual world and being able to recognize things in the environment, even being able to interact with them in some limited ways. And we'd like to understand how that progression is happening. And the unspoken hope in that quest is that by understanding visual development, we would be understanding more than just visual development. We would be understanding some general principles of learning in the brain. So that's the long answer. One addendum to that answer as to why I chose to focus on vision. One addendum is that from a very early age, from my childhood, I've been interested in the visual arts. I'd love to draw and paint. And that interest also made me gravitate towards the study of vision. Because if you think about what is the primary thing an artist is trying to do, the artist is trying to put down on a piece of paper or on a canvas some information that would convey, say, the essence of the object that he or she is trying to capture. So the artist is essentially asking this question: what is the minimal information that I need to put down on this canvas so that an observer can understand what it is that I have drawn or painted? And that's almost exactly the same question that a visual neuroscientist would ask. What is the information that the brain needs in order to understand the world? So that interest in the visual arts also drove me to an interest in visual neuroscience.
That's a really fascinating journey because the brain is also very complex in the way it works. And from an infant age, how it learns to see, how it learns to adapt is very different for each person. So that's very interesting. And this field also is very vast because of that diversity, right?
Mm-hmm.
So my next question to you is, what are some of the biggest questions as you, as a researcher, are trying to answer about how the brain learns to see and in neuroscience in general?
Yeah, that's a big question. There's so many interesting open questions in neuroscience broadly, but even in visual neuroscience in particular. I would say one of the most fascinating questions, at least to my mind, is how it is that we get to be so data efficient in our learning. And what I mean by that is, if you think about the recent advances in artificial intelligence, the outcomes are very impressive. You interact with a vision language model or a large language model, and it's really quite impressive how well these systems seem to understand what you're asking of them and even the world knowledge that they possess. But if you look under the hood, you find that the amount of data that has been used to train these systems is immense. It's it's interesting that people are now wondering how we are going to continue training these systems when we are essentially exhausting all of the information on the net that's available. So that's the amount of information these systems need in order to have this simulacrum of intelligence. Humans, on the other hand, even if you talk to a 4-year-old, you get the sense that this little child has a decent understanding of the world. This little child can carry forth a conversation with you, oftentimes very intelligent conversations driven by curiosity and such. So a very interesting question is, how is it that the brain can make do with so little training data, whereas artificial systems that are trying to accomplish similar things require so much more? So what kinds of regularities from the environment is the brain picking up on that allow it to be so data efficient? So I would say that that's one of the biggest challenges in our field.
Right. So I also know that while you do a lot of research like on this kind of run, you also are running something called Project Prakash, if I'm
Mm-hmm.
not wrong. So can you
Yep.
tell our listeners a little bit about what that is
Sure.
and how that really started?
Yeah, so Project Prakash is an effort very close to my heart. We started it over 2 decades ago, and it ties in very nicely with this broader theme of understanding the brain and more specifically understanding visual learning. So one of the challenges in empirically or experimentally understanding visual learning is that it happens so fast. So as I was saying, even within a few months, a baby progresses from being largely helpless to being a fairly sophisticated observer of the visual world. And that rapid progression makes it very difficult for us to understand what are the milestones, what are the principles that are unfolding in those first few months. Because in order to do any kind of empirical work, you would need to work with, and newborns, of course, are notoriously difficult to deal with. Not only are they not interested in being an experimental subject, they have very limited comprehension of what you are asking them to do, and they have very little by way of a response repertoire for you as the scientist to understand what it is they're experiencing. Furthermore, there are many developmental and maturational processes happening in the baby brain at the same time. So attentional systems are developing, memory systems are developing, the motoric systems are developing. So it becomes very hard to titrate one kind of developmental progression from all of these other ones that are unfolding at the same time. So in my lab, as we were getting started here at MIT, we were coming up with this conundrum that we are interested in this question, but we don't have a good way forward for addressing, experimentally addressing, what are the initial stages of visual learning. Around that time, and we're talking about, say, the early 2000s, so around 2002, on a trip to India, I completely by chance happened to come across two children who were begging on a street in Delhi. And both of these children, I noticed, had blindness, and blindness of a form that, even though I'm not an ophthalmologist, I could tell that this blindness is treatable. So this was blindness caused by cataracts, which is essentially an opacity of the lens. I had only ever seen cataracts in people who were quite old, so say 75 or 80-year-old individuals, in whose eyes the lens would, just by the normal aging processes, begin to go opaque. And then people would get fairly straightforward surgeries. But what I was seeing with these children was that these were children who had been born with cataracts. So in the moment when I met these children, it was viscerally powerful to see that children would have this double whammy of not only being very poor and having to beg, but additionally to have blindness, and a kind of blindness that seemed needless. They ought to have been treated, but they obviously had not been. So just on a human level, it felt to me that something ought to be done about this. We ought to be finding such children and providing them medical treatment. But the challenge there was, how do we provide this kind of treatment to many children, not just one or two, but realizing that this condition was fairly widespread? How can we have a more robust program of providing such treatments? And as I was pondering that question, I realized that in providing medical care to such congenitally blind children, we would also have an interesting way forward on the scientific question that I had been grappling with. Because you can imagine that if you have, say, a 10-year-old child who has been born blind, and you are medically able to initiate sight in such a child at that age, then from those very first moments of the bandages coming off, you have a ringside seat onto the process of visual learning. So it was almost a perfect coming together of a humanitarian need and a scientific opportunity that would allow us to address some very interesting and important questions in neuroscience. So with that realization that there's this dual theme that can be pursued here, I approached funding agencies that were science-oriented funding agencies. And I described to them what the scientific opportunity here was, and also what the possibility of humanitarian intervention existed. And the agencies responded very favorably, and we got funding for this work, and that's how we got started.
It's been a long journey for you. I can tell because even when like we also live in India and we see a lot of this on the road as well, and we don't really know what to do about it. And what you have done is really amazing and transformed so many lives. And learning how to see is something that's so fundamental for children that it's a really important work that you have done. So
Thank you,
that's
Nikhil.
really amazing.
Thank you.
So through your work and research, I want to understand like what has been something that's very surprising or significant that emerged from your research? What was something that really, took you off your feet and was like, oh wow, this is something really interesting.
Uh, yeah, so there have been many gratifying results to emerge from Prakash. One of the first ones was the observation that children, despite having been blind for the first several years, they are able to acquire significant visual function when they gain sight, say at the age of 10 or 15, or sometimes even in the early 20s. And the reason that was surprising is because there was this general belief that the plasticity of the brain, the ability of the brain to change in response to external input, it's a rapidly declining resource. We have a lot of plasticity as infants, but then as we age, that plasticity, that resource begins to decrease. And by the time we are in our pre-adolescent years, we have essentially completed that period when we are learning to see, learning to make sense of the world. And the kind of learning that happens after those initial years is more of this high level learning rather than the basic aspects of sensory learning. And these results, or this belief, was coming from a lot of really beautiful work that had been done with non-human subjects like kittens and mice, where researchers had found that the consequences of early visual deprivation. So if you take a kitten and say you suture shut one eyelid, so this kitten is now experiencing the world with just one eye open. Even if this period of lid suture is a fairly short one, uh, when the sutures are cut and the kitten now has both eyes open, the kitten behaves as if it's functionally blind in the eye that was temporarily closed. Uh, and it behaves that way for the rest of its life, suggesting that maybe there is a critical period for the brain to receive information from the eyes. And if it does not during that period, then forevermore the brain won't be able to make sense of visual information from the eye. So that idea, if you translate that to humans and to Prakash children, that would mean that past, say, the first few years, these children are essentially, you won't really be helping them. Even if you correct the eye, even if you take out the opaque lens and you implant a transparent lens, the brain simply won't have enough plasticity to make sense of the world. Uh, so we started with that somewhat pessimistic outlook that maybe even though we are trying to help the children, we might not succeed. The brain simply won't have the adequate resources. But to your question, Nikhil, what was a surprising observation? To our surprise, we found that even though some important aspects of vision do seem to be permanently compromised, uh, consistent with the notion of critical periods, many other aspects of visual function can be acquired even late in life. So the distinction between functions that are permanently compromised and those that can be acquired is mostly at the level of functionality. So low-level aspects of visual function, things like clarity of vision, those are seemingly permanently compromised in the Prakash children. So whereas you and I have 20/20 vision, which simply means that at 20 feet, so if I am normally sighted and I have 20/20 vision, then at 20 feet, I can resolve patterns that an average human being can resolve at 20 feet. If I have worse than normal vision, then the denominator goes up. So let's say a 20/100 vision means that I would need to be at 20 feet to be able to resolve what an average human can resolve at 100 feet. The Prakash children uh, invariably have worse than 20 over 20 vision. So they might have 20 over 100, 20 over 200 vision. So there is clearly an important role that early visual experience plays. But remarkably enough, even with this degraded clarity of vision, the brain of a Prakash child is able to make sense of the objects in the environment. They are able to begin to recognize objects in the environment. They're able to navigate the visual world on their own. They're able to recognize people. So there's a lot of learning that still seems feasible, indicating that there's a lot of plasticity that still exists in the visual brain. Um, and even aside from behavior, if you directly look at brain activity and how that activity changes as a function of time, using techniques like electrophysiology, so EEG, or functional neuroimaging, fMRI, you find that the functional organization of the brain is undergoing massive changes in a matter of months following the onset of sight. So that evidence of significant plasticity that was revelatory for us, and it was very important, as you might imagine, from the applied perspective, because it suggested that providing surgeries even late in life, even into early adulthood, is something worth doing. If we had found that surgeries past a certain age don't help, then it becomes a moot point. Instead of exposing children to the risk of surgery, we ought to be providing them palliative care, things like braille and white canes and such. But the fact that surgery does in fact help, that has important policy implications.
Okay, so a lot of the work that you've done with Project Prakash has helped you kind of understand early visual experience, first sight related
Hmm.
it has implications for the visual brain plasticity, which means that, well, there is some light at the end of the tunnel sort of situation is what
Indeed.
I'm getting the idea
Mhm.
of.
Yep.
Right. So accounting for this, and now we're coming to the modern world. You spoke earlier about artificial intelligence, LLMs, the kind of stuff
Hmm.
that is really in the newspapers and the media taking
Hmm.
over everyone's
Hmm.
mind space right now. So, how do you think research on the human brain is shaping the future of artificial intelligence? Or maybe you consider that vice versa. I don't know. But what's your opinion on the connection between the two?
Yeah, I think it is this bi-directional dialogue. So our work in terms of formulating hypotheses about brain function have been facilitated by work in AI. And conversely, we believe that some of the experimental results we are getting from the newly sighted children have something to say to the AI world. I'll give you one example of this directionality from the experimentation to AI. And it relates to the point that we were discussing earlier about the incredible data efficiency of the brain, how it is that even with fairly limited uh, data, we are able to do a lot, and we have significant robustness in our ability to deal with very variable visual inputs. Um, so the question to us was, how does the brain accomplish that? How does it get that robustness? And based on some of the experimental results from the newly sighted children, the hypothesis that we have been pursuing is that it may well be that the developmental choreography that the brain goes through is responsible for the eventual robustness of the brain. So what I mean by that is the following. So, Aashna, I believe at the outset you had mentioned that there is diversity across humans and how we develop. So that's certainly true. There's a significant amount of diversity, but there's also commonality in our developmental progressions. So you, Nikhil, I, everybody else has gone through a certain set of changes as we have matured from babyhood to our later childhood years and to adulthood. So one of the early aspects of vision in infancy is that the clarity of our vision. So I was talking about this 2020 vision that we have, or many of us have as adults. We start out as babies with really poor acuity. So a baby's acuity at birth could be as bad as 20 over 600, or even worse. So this is worse than what the WHO classifies as legal blindness. So we start out with really crummy vision. And then over time, over the first 2 or 3 years, this acuity improves until we get to close to 20/20 vision. Now, this reduced acuity at the outset has often been thought of as a limitation of biology, that biology simply is unable to give us very high acuity at the outset because our photoreceptors and our neurons are very immature, and hence it's an inevitable consequence of that immaturity that we start out with really poor vision. And only as the neurons and the retina matures does our acuity get better. If biology could do a better job, then maybe we would have started out with better quality vision. But the hypothesis that we are entertaining, based on results from the newly sighted children, who bypass some of these early maturational changes. The hypothesis is that these early degradations that the brain is having to contend with in the developmental timeline are not impediments, but rather scaffolds for its later proficiencies. So the fact that the brain has been exposed early on to these really crummy images, low quality, not very colorful, because the cones in our retina are immature. Those degradations actually help the brain put in place algorithms and representations of the visual input that allow it subsequently to perform really powerfully and robustly in the visual world. So we are hypothesizing that it's this early developmental experience that has rendered the right kinds of algorithms in our brain so that when it comes time as adults to deal with degradations, we are able to rely upon that early learning. So, what that means for AI systems is that following a training regimen that mimics the developmental progression that humans go through might actually be beneficial for helping these AI systems also exhibit similar kinds of robustness. The conventional training regimen for an AI system would be just bombard the system with high quality images right from the get go. And in fact, if you if you worked with, say, convolutional neural nets or any other kinds of deep nets, that is the standard procedure. You have just a whole bunch, millions of high quality images, and the system is being trained on these high quality images. But if our hypothesis is even partly valid, it would be better for such a system to go through this initial period of degradation and only later be exposed to high quality images. And in some of our computational simulations with deep networks, we find evidence to corroborate this prediction that networks that are trained with this developmentally biomimetic training regimen perform better than networks that are trained with high quality inputs. So that's one example of how looking at the human system or the biological system, and specifically the developmental progressions, can help us derive some insights that might be beneficial for artificial intelligence systems.
That's really amazing because we're going from the data that we have and helping artificial intelligence also become better while we're also gaining insights from it. So it's really amazing how it's a two-way street. We usually look at it as mostly a one-way street where we're getting a lot of things from it, right? So
Mm-hmm.
we've talked a lot about your projects, the research that you've done, and it's very deep. But now let's take a look into the future. So I want to ask you, where do you see the field of vision, neuroscience, and AI all together heading over to the next decade? And what are the biggest challenges
Hmm.
that you think that still remain?
Yeah, so I think I would say that we have already made a surprising amount of progress uh, in getting at some of the basic principles of visual function. And even though one can be critical of some aspects of, say, the machine vision systems, like their data hunger, it can't be denied that the kinds of capabilities they have come to possess are very impressive. Uh, Even just 15 or 20 years ago, the vision systems that we had were much worse than the vision systems that we have today. In fact, in many aspects of visual function, AI systems are now exceeding human capabilities. So when you think about, say, autonomous driving systems, yes, they have their failure modes, but by and large, they have accomplished a lot. So, given where we are, what might be the frontier areas where these systems can go and where the study of biology can help, I would come back to the efficiency point. So, data efficiency and energy efficiency. On both of these fronts, biology still has a significant upper hand. Uh, we are able to do a lot with very little. So, in terms of how much experience we need before we are able to acquire our very robust perceptual capabilities, that's quite remarkable, quite different from machine based systems. And in terms of the energy requirements, the difference is perhaps even more stark. You might have heard of how there is resistance to AI data centers in different parts of the world because they are so resource hungry. They require a lot of energy. In fact, some companies are even thinking about setting up nuclear power plants to power these AI data centers. And even just to cool the chips in these systems, the amount of water that's needed is incredible. Contrast that with the kind of energy needs that the brain has. So the human brain essentially uses the energy requirements of a 20-watt light bulb. With that little energy, we are able to do all of the impressive things that we do. So understanding how we accomplish so much with so little, both on the data and the energy side. I think these are going to be two of the big frontier areas in the coming years. On the more human side of things, understanding how not just how uh, typical development progresses, but also how this development can go awry. What are the modes by which there might be atypical kinds of development that lead to conditions like autism or childhood schizophrenia and others? That I think is going to be very important. It's going to have a huge, big impact, not only on basic science, but also on millions upon millions of families. So I would say that that's another very important area to target.
It sounds like there are a lot of open threads in neuroscience that are just waiting for people to explore in some way. And
Absolutely, I would say.
I think you've painted it as a very appealing view of the field because I know a lot of students really find neuroscience fascinating because, like me, the complexity of it, the fundamental sort of questions that
Mhm.
arise from studying that field, it's very thought-provoking. But that being said, it also feels like an intimidating field because I'm like, you have to think about how people think. How did that even develop? Like, it feels very abstract, very out there in some way, right? So, for students who are interested in this kind of field, what do you think they should do right now to prepare themselves if they want to pursue something like this as a career?
Mhm. Yeah, so the good news is that there's a lot of information freely available all across the world for anybody who's interested in brain science to get acquainted with the field. There are many courses on platforms like edX, Coursera, and so many others. There's so many interesting YouTube videos that are very creative, but also very informative. So I would say to start out, students who are interested in this topic should just acquaint themselves with, say, an introductory course in something like perception or cognitive science. And based on that introduction, which is going to be more like a table of contents or about many things that the brain does, once a student has a sense of across these many different dimensions of brain function, these are the two or three that really appeal to me, whether it's motor function or language or perception, then dive deeper into that topic again, look at some of these courses that are available. And with that understanding, think about, say, defining some projects that one could do as an independent project, or one could do as part of a school enterprise. Uh, I'm sure teachers in any good school would be very willing to act as resources, as mentors, as co-discoverers of knowledge in specific subfields of neuroscience. And the reason I'm talking about projects is there's nothing quite so engaging about a field as discovering new knowledge yourself, or even rediscovering knowledge that others have discovered, but with your own hands. So engaging in a project, whether it's replicating past work or it's breaking new ground, it can be a very nice way of really getting your hands wet in the field and making sure that this is a domain that you want to pursue further. Or maybe you discover that, yes, it's interesting, but it's not something that's entirely to my liking. But that kind of realization only comes in when you really engage with an area, uh, with a project of your making.
I think that's very tangible advice for a student to take forward, and I think you've broken it down into steps. So I know I'll definitely go down that path, and I'm sure some of our listeners will too. Thank you for
Cool.
the advice.
Oh, certainly.
Yeah. Now coming to our last question, I think our listeners have learned a lot from this, and we just wanted to ask you, what is one thing that you want to leave our listeners with? What is something that you want to say to them? What's your message?
Ah. Well, I would say the two things, just reflecting on what's been impactful for me. So one is being open to change. So when I was describing my trajectory through science, even though I initially thought that I would be a computer scientist, but eventually my path veered towards neuroscience. And that openness to change is something that should not be feared. Rather, one should always be willing to change course if there's a little voice in you that's indicating that maybe this is not something that I'm really passionate about. So a little bit of that fearlessness and courage to change. That's important. And no matter what stage one is in, whether one is in school or whether one is in graduate school or even a faculty member, that openness to change is only helpful. That's one. The other, I would say, is when you're trying to figure out what is the question that I ought to be pursuing, thinking about, so starting from the very highest level so as to be able to identify big problems in the world. So instead of starting from a very specific paper and trying to figure out, okay, exactly what did the paper do, and let me now define a project that makes some minor tweak on the specific question that this paper has asked. Instead of that, start at the other end. Start by understanding what are the big things that the world needs. And there are resources for helping you get that understanding. The UN has the Sustainable Development Goals, the SDGs. So they have, and many people have already done a lot of the groundwork to identify what are some of the biggest challenges. So starting there and figuring out what are some of the specific things that I can do to address these big problems. I think yoking your life to a big question, it keeps you motivated. It helps you understand why it is that you're doing what you're doing. I mean, life is precious. One has only so many years in one's life, and one always needs to keep in mind how one's life uh, at least has the potential to make a difference. And one gets that sense by starting from the big picture and then drilling down to the more specific one. So those would be my two messages: the fearlessness in being accepting of change, and starting from the big questions.
Those messages are really inspiring. And the whole interview today was really insightful, and getting to learn about your journey has been really like I was awestruck by listening to your journey in your project. And I would like to thank you so much for being with us, speaking to us, answering our questions, and helping us get an idea of the field of biology, neuroscience, and vision, and giving us inspiration through your initiatives in this field. We're very grateful for your time and your contribution to our magazine and initiative. Thank you so
Thank
much.
you very much, Nikhil. It was a pleasure to chat with you and with Ashna. And all the
Thank you
best
so much.
for your work. Uh, and I hope our paths will cross again at some point.
Thank you, sir.
Great. Thank you.
Thank you for joining us on this journey of ideas, inspiration, and innovation.
We hope this conversation sparked curiosity and reminded you that behind every great discovery is a human story of passion, purpose, and persistence.
Until next time, stay curious, stay inspired, and keep learning, because the future is being built by the questions you asked today.
This is Dialogues of Discovery signing off.